Good morning, students. So we are doing the discrete time Markov chain. So let us today do the mean time spent in the transient states. So if some states are transient, so we know that these states are visited finitely many times. So finite times. So therefore, let us determine the sharing the screen. Okay, so let us determine the mean time and in transient state. So we have a finite state Markov chain. So let us say some states are there. So because if a finite state, so therefore some states will be recurrent, at least one state will be recurrent. So some states are maybe transient also. So let us say that we denote the set of transient state by 1 to so on to t, capital T. So this is the set of transient states. Okay, now let us from the TPM we separate out the values for corresponding transient states, so that we are writing down P11, P12, P1T, so on, PT1, PT2, PTT. So this is the basically corresponding to the transient state, the corresponding values of the TPM we have taken, that we are denoting by PT. So clearly sum of rows will be less than 1, otherwise T becomes a closed set. Okay, so therefore let us say that I and J belongs to the set of transient state, and we denote by Sij the expected number of time periods that the Markov chain is in state J, given that it starts in state I. So we are saying that this is the expected number of time periods, the Markov chain is in state J, given that we are starting state I. So both are transient states, let us say. So we want to determine Sij. What is the value of Sij? So let we denote by delta Ij as 1 if I is equal to J, 0 otherwise, and let us denote I n comma j as 1 if the process is in state J in nth step, 0 otherwise. Now Sij is the expected number of time periods the Markov chain in state J, given that we start in state I. So this will be at 1, it will be 1 if I is equal to j, and 0 if I is not equal to j, plus expected number of time periods plus basically how many times we are in state j, n is 1 to infinity, given that we start in state I. So this will be at least 1 if delta I is equal to j, because we are starting there itself, plus this value. Now this will be delta ij plus summation n is from 1 to infinity, expected value of I and j, given x naught is equal to I, because we can take the expectation inside here, plus is equal to delta ij plus summation n is from 1 to infinity, but I and j is 1 if xn is equal to j, 0 otherwise. So therefore this will be probability 1 into probability xn is equal to j given x naught is equal to I, plus 0 into probability xn is not equal to j, given x naught is equal to I from here. Okay, so therefore this will be delta ij plus summation n is from 1 to infinity p. This is by the, because this is the transition probability, we are moving from state I to j. Okay, this is basically xn equal to j, because from here, so this will be pij n basically. Now we know that pijn by the Chapman CK equations, this can be written as summation k pik pkj n minus 1, using Chapman-Kolmogorov equations. This is this value. Now, therefore, this value is delta ij plus summation over k pik summation over n is from 1 to infinity pkj n minus 1. Now, this will be delta ij plus summation k pik. Now, when n is equal to 1, then this becomes pkj 0. And pkj 0 means we are in starting from basically probability that xn x 0 is equal to k, given x 0 is equal to j. So this will be 1 if k is equal to j, 0 otherwise, for n is equal to 1, and this is summation n is from 2 to infinity p kj n minus 1. Okay, when n is equal to 0, n is equal to 1, this value is pkj 0. That means probability that x 0 is equal to j, given x 0 is equal to k. So that will be 1 if k is equal to j, 0 otherwise. Therefore, this will be delta ij plus summation k pik delta kj plus summation n is from 1 to infinity, p kj, and take n minus 1 is equal to m, then replace m by n. So this is the value we are getting. So this value is nothing but from here star. This value can be written as skj. This value is skj from star. So therefore this value is delta ij plus summation k pik skj. Now this summation is for all the values over all the states which are possible. So, but we know that uh, if we have some recurrent states and some transient states, let us say something like this. Okay, so these are recurrent. This is transient. Now, from a recurrent state, we cannot go to transient state. If we allow that thing to happen, then transient state also become recurrent. So therefore, it is impossible from going from recurrent state to transient state. So therefore, summation k is from 1 to t, whatever the possible transient states are there, p ik skj. Since it is impossible to go from a recurrent to a transient state, implying that as kg is equal to 0 expected number of time periods, we go to Markov chain in state j starting from state k, where k is a recurrent state, that is 0, where k is a recurrent state. So that is the relationship we get, that therefore S ij is equal to delta ij plus summation k is from 1 to t p ik skj, where I and j belongs to the set of transient states. So any question till now? Okay, am I audible?
Yes, sir.
Okay. So now this is basically the expected time spent in the transient state Sij, starting from state I, time spent in state j. Expected number of time periods, that Markov chain will be in state j. Okay, so can we determine this in the form of matrix notation? So we can write S is equal to S11, S12, S1t, and ST1, ST2, STT. Okay, so therefore this can be written as S is equal to I plus PT S in the matrix notation, where PT is the set of TPM of the transient state. Okay, so now from here I minus PTS is equal to I, so which implies that S is equal to I minus PT inverse. So therefore, to determine the value of expected time spent in the transient state, starting from some transient state, we have to determine I minus PT, take the inverse of that and find out the answer, and corresponding Sij value will be in the S matrix. So let us take an example. Consider the gambler's ruin problem with P is equal to 0.4 and N is equal to 4, starting with 2 units. Determine the expected amount of time the gambler has 3 units. B, the expected amount starting with 2 units, expected amount of time the gambler has 1 unit. So the gambler's ruin problem, you know that some state is there. So therefore 0, 1, 2, 3, 4. So you can go here. Probability P, Q, P, Q, P, Q. Okay, and also one here. So this is the basically gambler's ruin problem here with P is equal to 0.4, N is equal to 4. So now that means starting with the in each step gambler is basically betting 1 rupee with probability P and losing 1 rupee with betting 1 rupee. He's gaining 1 rupee with probability P, losing 1 rupee with probability Q. And when he is in state 0 and 4, he will stuck there because his aim is to achieve 4 rupees in this case because N is 4 here. So corresponding value of this is the TPM. So which are, first of all, can anyone tell which are the transient states here, which are the recurrent states here, and recurrent or absorbing? So what are which states are communicating?
One to one.
Yeah, 1, 2, and 3 are communicating, so they are in one class. 0 in separate class, 4 is in separate class. So these are the equivalent classes. Now 1, 2, and 3 basically, because your transient state is visited finite number of times, and recurrent class is visited infinitely often. So you can see if we are in state 1, so we can be in state 1, 2, 3 finite number of times. In final, it will either go to 0 or 4. So 1 is basically transient. So therefore 1, 2, 3 are transient, and 4 is absorbing or recurrent, because something is going in, it cannot come out. So 0 is also absorbing and recurrent also. Okay, so therefore uh, these are the states. So set of transient state is 1, 2, 3 here. Okay, so this may be different also. Then what is the corresponding TPM? 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So this is 1, 0, 0, 0, 0. Now this is 0.4. What is the value? Okay, P is Q is 0.6. So 0.6, 0, 0.4, 0, 0, 0, 0.6, 0, 0.4, 0, 0, 0, 0.6, 0, 0.4, 0, 0, 0, 0, 1. So from here we can separate out PT, because 1, 2, 3 are here transient. So corresponding to 1, 2, 3, this matrix we can separate out. So this is PT. So PT is 0, 0.4, 0, 0.6, 0, 0.4, 0, 0.6, 0. Okay. Find out I minus PT. So this is I is 1, 0, 0, 0, 1, 0, 0, 0, 1. So 1 minus 0.4, 0. Okay. So I think everybody knows I is basically here 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So 1 minus 0.40 minus 0.6, 1 minus 0.4, 0 minus 0.6, 1. Find out I minus PT inverse. So this is 1.46, 0.76, 0.31, 1.15, 1.92, 0.76, 0.69, 1.15, 1.46. So this is I minus PT inverse. So this is basically S. So what we need is basically S23. This is 1, 2, 3, 1, 2, 3. So S23 is 0.76 and S21 is 1.15. So we have got the answer that X starting with state 2, the expected amount of time gamblers spend in state 3 is 0.76. Starting with state 2, expected time the gamblers spend in state 1 is 1.15. Okay, so this is the now. So let us determine the starting with state 2. What is the probability that gambler has fortune of 1? So same example, continued. So now in the gambler's rule problem, starting with state 2, what is the probability that the gambler ever has a fortune of 1? Starting with rupees 2, what is the probability that gambler has rupees 1? So what we have to determine, can anybody tell in notation form? This is F21 starting with state 2, first visit to state 1. Okay, or gambler ever visit to state 1. So F21 basically for this example where P is 0.4. In the last class we have done the same example we have taken. So P we have taken 0.4 here. So F21 is 0.78 from here. Okay, so F21 is 0.78 from here we have done. Can we determine this using the expected number S value? Okay, so this is F21 is 0.78. So we have done already this. So can we determine this? So so what is Fij? Fij is the probability that the Markov chain ever makes a transition into state J given that it starts in state I. So Sij is the expected time in J given that we start in I. So using law of total probability, this is expected time in J given we start in I ever transit to J into probability Fij plus expected time in J given we start in I never transit to J into probability that we never transit to J, 1 minus Fij. Okay, now this is so this is delta ij, first one, plus expected if we are in state I is equal to j, 0 otherwise, plus expected time in j, we start in j, okay, plus sij, sjj, because we basically delta ij is basically that I is equal to j, 1 0 otherwise. So that means when we move to j, we are in j basically, so expected time into plus expected time in j, given that we start in j, because it will forget the past because it is a Markov chain. So that becomes sjj into fij plus expected time in j, given we start in I, never transit to j. If I is equal to j, then this is 1, otherwise this is 0 into 1 minus fij. So therefore delta ijf, so therefore this value will cancel with this value. Okay, so we are left with delta ij plus fij sjj. So this is the value we are getting. So therefore this implies that fij is sij minus delta ij upon sjj. So example, let us say this is u. So example u. So because S31 is yes, S, we want to determine our F21. Sorry, yeah, we want to determine F21. So this will be S21 minus delta 21 upon S11. So S21 we have already determined 1.15. Delta ij is, because 2 is different, 2 is not equal to 1, so therefore this will be 0 upon what will be S11. S11 is 0, S11, 1.46, 1.46. So how much is the answer? 0.78. So we have determined this basically by 3 methods. One is this. Another one was by direct method we have determined this example. Another is we have determined using Gamble-Swin problem. Okay, so this was the, so any question till now?
So can you explain that delta Ig plus Sjj once again? Like how did you write it?
Yeah, because delta ij we have defined as this value. So if I is equal to j, this is 1 0 otherwise. So From there, if we are writing delta 2 1, that will be 0. Okay. Another was how we are writing S21 and S11. So S21 and S11 are values of this. S is equal to I minus PT inverse, values of this. This is nothing but all the values of Sij. Is it your question? Is there?
No, so like in the proof, like time in J, start in I ever transient to J, how you're writing in delta Ij plus Sjj. That is.
Okay. So this basically your question. Okay.
Yeah, yes.
So because first of all you note down that we are doing the discrete time Markov chain. So therefore the process will forget its past basically. Okay. Given future, given the present and past, the process will forget its past value. The future will given the present depend on only present only. Okay. So therefore this this value is this will be basically 1 if I is equal to j, 0 otherwise. At least one time with this will be this. If I is equal to j, this will be 1. If I is not equal to j, this will be 0. Plus expected time in j, given that we are starting with state I and at n dash step we are in state j, but it is a Markov chain, it will forget this thing. So therefore this is given that time in j, given that we start in state j. So that is nothing but definition of sjj.
Yes,
Is
sir.
it okay?
Yes, sir. Thanks.
Okay, now so this method can also be determined to use if some statements are there, they take some time to execute, okay, in a computer program. So we can determine the probability that group of statement is basically taking some time to execute. So some probabilities will be there. Okay, so based on that, we can determine when what is the average execution of the program also. So in computer science also we can use this type of concept where we can find out the average execution time of the some program also. Okay, so now let us now start with the branching process. So let each individual by end of its lifetime produces j new offspring with the probability pj. So this is producing j new offspring. Okay, so each individual by the end of its lifetime produced j new offsprings with probability pj which is less than 1 for all j greater than 0. So this each individual let independently of number produced by the other individual. So some other individual is also there. So it is producing individual independent of the other individual. So let independently of number produced by other individual. So let us say x naught is the size of zeroth generation. So x1 is the all size, basically size of the offspring of zeroth generation. All offspring of zeroth generation, or basically this is the first generation. Okay, and then we have xn is the size of nth generation. So basically we can start with, let us say some person is there, his how many sons he has, that is the, this is the zeroth generation, this is the first generation, then all the offsprings of these form the second generation, in that fashion basically. So xn is the size of nth generation. So what is the value xn can take? Xn is basically take value 0, 1, 2, so on. So this is the state space. Okay, whether it is a Markov chain, because size of the nth generation depends on the size of n minus first generation. It will depend on the n minus first generation only. How uh, n minus first generation has reached, that doesn't matter here, because xn depends on the x n minus 1, not how that n minus 1 has reached. So therefore clearly this is a xn is a discrete time Markov chain. Okay, now which states are recurrent, which states are transient? So you can easily see that uh, state 0 is recurrent, since zero member cannot produce offspring. If zero members are there in the uh, some generation, so it cannot produce offspring. So clearly F00 will be 1. That means starting with state 0, we are in state 0 for the first time. That will be 1. So therefore 0 is recurrent. Also you can easily see that if we are in first, if we have first one member, so next, in the next generation it may have either 0 or 1 or 2 or 3 and so on, because xn plus 1, what value it can take, that will depend on the Students, am I audible?
Yes, you are audible.
Yes, sir.
Okay, okay. So actually, electricity went here, so that's why mobile data I'm using. Okay, okay. So, okay, so now okay, I think my screen is now visible.
Yes, sir.
Okay, okay, okay. So now F00 is one here. So 0 is recurrent state. So other state, let us say we are in state 1. So xn plus 1, because Pij we have to determine. Pij basically xn plus 1 is equal to j, given x naught, xn is equal to I. So therefore, that value basically, if we take set of transient state, if we take finite set, 1, 2, 3 up to so on, so that state basically becomes transient. So we have seen an important conclusion here that the population will either die out or its size will converge to infinity. So either in the finally, either you will be in the recurrent state in the last. So either you will be state 0 or the size will becomes very large. So that is the conclusion we have made for this kind of discrete time Markov chain, which is known as the branching process. Okay, where individual is basically where xn is the size of the nth generation. Okay, now mean number of, let us say we denote mean number of offsprings of a single individual by mu, let us say, which is summation j pj, and variance of number of offsprings of a single individual we are denoting by sigma square. By definition, that will be summation j minus mu square pj. J is from 0 to infinity. So let us let we take x naught is equal to 1. That is, initially there is a single individual. Then xn is z1. Z1 is the number of offspring produced by the first individual plus z2 plus z xn minus 1. Why? Because xn minus 1 individuals are there in the n minus first generation. So where zi are the number of offsprings of ith individual of the n minus first generation. Okay, so therefore this is the value basically. The xn can be written in this form. So let us stop here. So what are the applications of this branching process? Application will lie in the neutron chain reaction. Okay, so where because some nucleus is there, some neutron is basically striking this. So then some additional neutrons are produced that will again strike to some nucleus. So basically, Xn we can take the size of the nth generation. So how many neutrons are produced in the nth generation? So there we can study this. Then electron multipliers. So where let us say some we want to amplify the weak current of electrons. So then some electron is hitting the electron plate, then it will producing some extra electrons. Then again those electrons are hitting to the electron plate and then producing another set of electrons. So Xn is basically the number of electrons in the nth generation. Similarly, in the survival of family names, so whether the family name will be survived if someone is producing some children's. So these kind of applications are there for the branching process. Okay, so any question is there? So next time we will continue from here. So we will find out what is the expected value of Xn, variance of Xn, all these kind of values.